So this seems like sort of a token climate talk at the end of a lot of discussion of earthquakes, the threat of that for Chile, and the social science work that's been done around that. But really the points and the issues for creating climate resilience are very common to what's already been discussed across all of the previous talks. So I'm really grateful to the previous speakers for setting that stage. Really what's unique here is the risk, is the climate information. And so that's primarily what I'm going to be presenting here. So in the interest of climate resilience, again, a lot of the topics that were discussed previously are relevant here also. But the difference, I would say, with climate between earthquakes, so earthquakes is more sort of a standing risk. You don't know exactly when they're going to come, but you are quite certain they're going to come at some time somewhere in Chile. We have more ability to look forward with climate. And so usually, although there's a preparedness aspect, it's often in this kind of climate proofing, sort of very similar to the earthquakes. You know, can we make sure that if we get those anticipated shocks again in the future, or they're changing in the future, that we'll be fine. And I really think that what we've learned over the last couple decades of working on this problem is certainly that there is an adaptation element to it, but preparation is critical as well. And it's not just climate change, it's across timescales. So in terms of some of the resilience measures, certainly engineering and infrastructure, there are solutions there that can be very helpful for climate resilience, but it's also one of these dynamic risks and dynamic resilience sort of issues that we need to take on. And so resource management is one that really is changeable over time, and that the actions and the preparedness, the adaptation that you might want to implement on shocks that you're facing over the next few years might be different than they would be 10 years ago or 10 years from now. Similarly, resource programming, right? Fiscal planning happens pretty much on an annual basis, making sure that you have the right people or resources in place to anticipate a disaster or to help people get through a shock is extremely important as well, and that's something that can be influenced by climate information in a dynamic level, and we need policy definitely to undergird all of that. So I'd like to show you one example from agriculture in Jamaica, and where this came from. This is obviously just one sector. So in Jamaica, as in many developing countries, they're putting together these national adaptation plans, and other countries have done this as well. So in Jamaica, they have this Vision 2030 set of outcomes. They've already done that, and the process behind that was to really talk to the country about what are the goals for where you see Jamaica in 2030, and what are the sectors that need to be involved in achieving those goals. And then they went through the next, so they took those sectors, and in this very large inclusive meeting, which was really focused primarily on government, started to break down the different inputs, outputs of those sectors. So what is it that contributes to having agriculture, for example, be resilient and be able to adapt through time? And so you can see in these yellow boxes, these are the inputs and outputs. So agriculture obviously needs energy, it needs water, it needs financial instruments. The crops and livestock are one input as well. And it needs the policy framework for all of that to hold together. They then looked at those different inputs and outputs and thought about what are the risks that those things face. And so that's what you see in these white boxes. The red letters, the red words, those are climate-related risks that these different areas are facing, and then the black words are other risks that they face. And so the point of having these sectors realize all of these risks together is the fact that those risks need to be faced holistically. And that's an important consideration, and that's certainly come up in the ideas of the previous talks. The other thing to notice, though, in the climate risks is that they are not, even though Jamaica is a place that's actually faced pretty substantial climate changes over the last several decades, they're not focused necessarily on climate change. They're focused on climate and how the weather may be influenced by the climate. So climate resilience is not just about climate change. We are not resilient to climate today. And it doesn't matter if you're in Jamaica or you're in Germany, that's the case. So we really need to take this quite seriously. All the climate that we face across timescales, how the large-scale climate is impacting the weather, because that's what impacts society and our livelihoods and our sustainability. So in the case of Chile, I've picked a location very close to here, very close to Santiago. And what we're looking at is for the rainy season, May through September, how has the rainfall varied over the last 27 years? So starting in 1980, this is the seasonal average rainfall changes coming to present. And we see, as those of you from the area know, the persistent drought, year after year of drier than normal conditions that have been observed and experienced in this part of the country. Now, I understand from one of my local colleagues that actually it's been even a more unprecedented situation in southern Chile. But this is what's been happening here, and it's very common human nature to perceive these sorts of changes as trends. I mean, it is, almost 30 years. But trends really take a very long time to discern. So is this actually the arrival of climate change? Is this what Chile can expect more of in the future? What is the longer timescale context of this? And so I would like to break that out. So in terms of the climate information, looking back at what's happened over the past, and in that setting I'm going to break things into different timescales just to address the issues, and in part because our ability to predict or project those changes actually is acting somewhat differently on these different timescales. And then, those tools that we are using to look forward, what do we have, how good are they? And then going back to how this climate information fits into the big picture. So I would like to use this globally average temperature as an illustration because you're going to see a lot of this, what I call timescale decomposition. And so I just want to, I think people are a little more used to looking at globally average temperature because it's just everywhere in the newspaper, on the news. So what we're seeing here in the black line at the top, this is over the 20th century, annual means, the observed temperature over land if we average that everywhere. So we consider this a globally average temperature year by year, and you can see the obvious increase, but you see also a lot of variability about that. If we extract the long-term trend from that, not necessarily a linear trend, but the long-term trend, that's the red line. And then we can then remove that trend from that observations and effectively separate the, quote, natural variability into a decadal, multi-decadal scale component and a year-to-year variability. So we know that even at the global level, El Nino, which is a year-to-year phenomenon, for example, affects globally average temperatures. And what these numbers indicate on the side here is how relatively important were these different timescales to the 20th century globally average temperature. So trend has dominated our observations of globally average temperature, but even year-to-year variability is still about 1/4 of what was observed. And this may seem relatively small in the decadal, but if we look at the intersection of these two, actually psychologically and in the media, it's been quite important because this little upturn here where the decadal temperatures, the decadal scale temperatures were moving towards warmer conditions in step with the trend is a period when we heard a lot about the acceleration of climate change. And in the more recent period where the decadal timescale took a downturn, countering the continuing upward trend, we started hearing about climate change plateauing or a hiatus or a slowdown in global warming. But we see it's really just these timescales interacting together because we experience them all at the same time. Now, if we were to do this same decomposition at each point around the world and to look at what a map of these numbers, these trend numbers look like, not every place in the world has been experiencing trend as the majority of their observations. So these colors down here, so the globally averaged is looking at 65%. There's very few points on the globe that have been experiencing temperature trends at 65% of their experience. In some parts of the world, it's much smaller. But this is the spatial distribution of how relatively important trends have been for temperature. If we look at precipitation, it's a much different picture. Over most of the world for the 20th century, precipitation trends have been only a few percent of what was observed. Now, part of that may be due to the very poor observing networks in some countries, and actually those are getting even worse. But let's go through the different time scales. So this is trends, very small percentage for rainfall. When we get to the decadal scale for most of the world, explaining more around 20 to 40% of what was observed, and most of what we experience in the climate is in the year-to-year variability. So what does that look like for South America? I've carved out, because of the rainy season in Chile, you're welcome, I've carved out the May through September rainy season and looking at these three time scales. And you can see that over Chile, the trend in temperature, has been quite small, really. I was rather surprised. There is a notable component in the decadal, and we'll come back to this later. But again, most of the year-to-year variability is the dominant component. And for rainfall, again, and this may surprise you, especially in light of that earlier graph that I showed you, but at this long century scale, the amount of variability that's been in trends for even the rainy season has actually been quite small. There's some important decadal variability, and most of what we experience here is the year-to-year variability. So let's look at a time series again focusing on the Santiago region. And this is, to the extent that this data set is representing the observations in this region, this is what happened over the 20th century. So the full time series estimating that between 1900 and about 2005, so admittedly leaving off the last 10 years, the trend has been basically flat. There has been important decadal variability and even prolonged droughts and very substantial year-to-year variability. So what can we actually say about this going forward, and what are our tools able to tell us? Dynamic models, climate models, are really the tool of choice. They certainly are very useful for exploring processes and phenomenon, and in some cases they may be useful for predictions and projections as well. But of course they have their limitations, and it's very important to use those in a knowledgeable way. So climate change projections, this is from the latest IPCC report, and it's looking at the April through September season. That's just the season they do. How many people have seen this already? Wow, surprisingly few people. It is kind of hidden in an annex. But here's how you interpret these maps, because I know that the titles are super tiny. The top row is basically looking at the next 20 years. Then, 2015 to 2035, then 2046 to 2065, and then down here, the last 20 years of the 21st century. And what these maps are showing you is trying to give you some idea of the uncertainty. And this isn't qualified in any meaningful way. It's really just the collection of models. What's the range of answers coming out of all of these international models that are contributing to these climate change projections? And so they've decided to do this in sort of a percentile way. So 1/4 of the models have this climate change response, or drier. About half the models are hitting, this is sort of the 50% break-even line, and then 1/4 of the models are wetter than this climate change projection, and then evolving through time. What the hatching means, these lines through here, what that means is that this climate change answer that that percentile is giving you is not larger than the variability. You can't discern it above the natural variability in these models. Again, not even the observational system. So what it suggests, because you can see once you get to the 50 percentile, even out by the end of the 21st century, there's a lot of uncertainty over Chile. It's really just some small fraction of the models, but they are indicating a suggestion for drier conditions. That's what the climate change projections are showing you. So it's a very small number of models, and if you look at the time series over this whole sort of west of the Andes region, it's very much like we saw with the timescales decomposition. So the average, the long-term trend that's being seen in these models is actually quite minor, but the variability about that is substantial. And so in terms of climate resilience, that's what communities and ministries and businesses need to be prepared for. So let's move to another time scale, seasonal forecasts. This activity has been going on in a very serious way over the last certainly 10 years, arguably 20 years. And this is a very qualitative map. I could show you more detailed versions, but I think this gets the point across. In the red areas, that's where the seasonal forecasts, so saying something about the year-to-year variability the next 3 to 6 months ahead, that's where those forecasts are quite good. And that does cover mostly areas in the tropics and developing countries. The yellow areas are what we would qualify as somewhat good. And often what that means is that the forecasts might have information at a particular time of year or under particular conditions. And for Chile, which is mostly in the sort of yellow region, this is for rainfall, they're somewhat good. Most of that skill is coming during the rainy season, and it's coming during ENSO events. But that's useful information. That's information that people can use to better prepare. Where the real frontier is in understanding and predicting the climate is in this decadal variability. So there's this slow frequency variability due to changes. This is true for ENSO as well, as there's changes in the ocean temperatures. That pattern of ocean temperatures influences the atmospheric circulation, that influences regional climate. For decadal scale, you're just talking about slower processes in the ocean circulation, large areas of changes in ocean temperature patterns that happen over decadal, multi-decadal periods. And so the one that's relevant to this sort of eastern side of the Pacific, or the west coast of the Americas, is this Pacific decadal oscillation. And this was primarily identified in the context of North America, so that's why this PDO index, which predates more analyses, focuses more on the North Pacific and North America. But it has been identified since then that this pattern, and you can sort of see it here, so this pattern is showing you how the sea surface temperatures change during the positive phase of this Pacific decadal or the negative phase. So with warmer temperatures being in the tropics during the positive phase, but that's associated with cooler conditions in the extratropics. And so we do see some symmetry in the extratropics about what's going on in the tropical Pacific. And so this has been redefined actually slightly differently as the interdecadal Pacific oscillation, which treats more of the full hemispheric pattern. But there's quite a bit of similarity in the time series. And if we look at the time series of whether or not that variability was more in this positive phase, and these red areas are more this negative phase, we see that recently the PDO has been in a very negative persistent phase. This has certainly been associated with drought in California. And I will say that the studies that I've seen on the more hemispheric one, the IPO, have made associations with drought conditions in Chile as well. Although most of their statistical significance is for sort of central and northern Chile. But the other thing that's relevant to this as well is the reason that this was identified as important, that people even came across it, was because of the change in fish populations. It was actually changing dramatically the entire biological ecosystem off the coast of northwest US. And so it's quite possible, I haven't actually didn't find any good studies on this, but it's quite possible that the IPO has some influence over the coastal and marine ecosystems in Chile as well, which I think would be very helpful to understand and potentially better predict. And here's why. I think that that's actually one of the few places we might be able to say something in terms of temperature. So with the last IPCC report, one of the things that they took on was actually these experimental predictions of decadal variability. So using the exact same models that we use for the climate change projections, greenhouse gases are increasing into the future, and the only difference was starting the oceans in a state close to observations. So seeing that any predictable information about the next 10 years is likely in the ocean state and how that evolves, trying to initialize the oceans and so we can see if that carries forward any predictive information. And we can look at how much more skillful saying something about the next 10 years is if we initialize the ocean versus if we just use climate change projections we already had. And so that's what this set of graphs is looking at, is this comparison. This on the left here is in terms of accuracy for temperature and rainfall, and here in terms of correlation. So does the time series go up and down at the same time? So correlation for temperature and for rainfall. So just focusing on temperature here, we have a lot of increased accuracy in temperature, it appears, from initializing the oceans, and that's certainly important. But a lot of that is because the models have drifted away and we're just starting them at a more realistic point at the beginning of that 10 years. But you'll also notice that even so, there's very few areas that over land that benefit from that. One of them happens to be over Chile. But I think what's really interesting is in terms of this correlation, being able to say something about the ups and downs, this is pretty much the only region in the world that those models are saying something useful. And I think it's going to be very interesting to understand what those processes are that are leading to that. In terms of rainfall, it's just a mess. There's really very little to no skill that's being recovered over land areas. Most of these red areas where the initialized predictions are better are so small and noisy that I think you could easily argue away sampling variability. So there are ways to address that. There are statistical methods that really take the observations, and I'm not going to step through this whole machine of a statistical approach, but just to say that there are these types of statistical approaches, such as stochastic modeling, that are looking back through observations, assuming that you have a long history of observations, and at least trying to recreate a realistic scenario of what if those observations had played out just as they did in the past, but in a different order. So you're maintaining the size of those events, the persistence of those events, the covariance between temperature and precipitation, all of those things, which the models actually have quite a difficult time, especially with persistence. And then you can generate thousands of ensembles of this realization. You can treat trends on top of that in a way that makes sense for your particular application. And just to show you two examples of that, this is not done for Chile, this is done for part of the world that has a pretty discernible drying trend. You can start to look at, say, decadal variability out into the future. So targeting, say, a decade, 2040 to 2050, and looking at how does just this random playing out of decadal variability, here we're not even talking about it being driven by the Pacific, just random variability that happens to have a signature in the decadal timescale. In one case, double the expectation of drying trend from climate change. In the other case, completely offset it. And you can run these sorts of experiments through agriculture, hydropower, disease models, and actually look at the resilience of systems, natural and human-built, to see how resistant they are to those climate shocks over the future. So coming back to this example here, it went further to actually start to brainstorm on what sort of interventions in the dark pink could come into addressing just this one input of the crops, livestock, and fisheries. So again, looking at the climate shocks and what interventions could come in to address those. And then in the lighter pink, what are the agencies that are responsible for dealing with those? Now, again, these are focusing on government agencies because this was a government exercise. The one exception is you'll see that the university figures quite prominently even here, but certainly implied are, for agriculture, a number of farmer groups, NGOs, private donors, private sector, international donors, coming in to really make success in this. And this process is now caused the government to tell those different ministries what you need to do is get each of your ministries to create their own policy action plan to address climate resilience so that everyone is part of that solution. And so my final view graph here is really just thinking about, we've seen a lot of versions of these types of view graphs, but in terms of what can the government do about resilience and policy behind that, it's important to think about what are the responsibilities and where are you depending on information. There certainly are solutions that are coming out of the research sector, whether that's innovation hubs or the universities, private sector. Some of that will happen in collaboration, some of it will happen in isolation, and as they start to become more problem-focused and these ministries start to engage more with the people downstream that they're getting information from and that they're feeding information to, this is really that research space where you need the collection of experts and practitioners working together on a common problem. So in summary, although there's a lot of mention of climate change in Chile, the observations, at least that are available to the global community, suggest those trends have been very small. The year-to-year shocks really do dominate, and when you have persistent decadal scale changes, those year-to-year shocks can be quite devastating. Policy is certainly needed, that political will to make these changes happen, but that also needs solid science and research behind that. The climate information coming into that process has to be very good. And I'm going to come back to this term that's come up a few times, multidisciplinary and transdisciplinary, and to provide my definition for that. You need people who are experts in their field, absolutely. But you also need people that can speak a lot of languages and understand a number of disciplines. But all of those people need to be together. If everybody is just shallow in a lot of disciplines, there will be no innovation. If everyone is just deep but they can't speak to each other, you will also make no progress. So these things need to come together to realize effective solutions. Thank you.